Thank you very much. Thank you for the invitation. And Ram had assigned me to talk about pollution sources, and I'm happy to do that, but I'm giving my own twist to it. So it has been mentioned several times before, what can we do to avoid the problem? So what can we do to control air pollution sources? What can we do to control air pollution sources to improve health? So that's the thematic of this presentation. Now, let me first show you a global overview of particulate matter. And we're talking about fine particulates. So we call them PM2.5, particulates that have a diameter smaller than 2.5 micrometer. And this map has been derived from long-term satellite observations. Now, satellites cannot directly measure PM2.5, but you can infer it from these data. And you can see the dark areas, the red and dark orange areas are the areas where the air quality guideline of the WHO of 10 micrograms per cubic meter is exceeded. And if you overlay this map with a population map, you will easily find that more than 90% of the global population is exposed to levels that exceed the air quality guideline of the WHO. So we're talking about 7 billion people here. Now, the particulates do other things. They're also climate pollutants, as we have heard. And that's what I would like to show with the next map. So we use data from satellites, from ground-based stations, and we use models. And we have to combine these things to disentangle the information that we really need. What you see here is the radiative forcing of particulates, the same particles that cause air pollution. And you see some blue areas and you see some red areas. And actually some of the particles are cooling, that's the blue, and some of the particles are warming, and that's the red. And actually most particles are either both cooling and warming, and you have to sort of get the net effect out of it. And you need to know the environmental conditions, like the reflectivity of the surface, and the chemical composition of the particles to understand the optical properties. And if you put this all together, you get a cooling effect. So the bottom line here is that if you would be able to remove all the air pollution by particles, you would also remove this cooling. Only over the Sahara it would become warmer, but cooler. But in the rest of the world, when you remove the particles, it becomes warmer. So that's something to keep in mind and needs to be part of the discussion as well. Now, we use models. We use the methodology of the global burden of disease to calculate health impacts of these particles. But we must use models also to study which of the sources are responsible for what. And of course, if we have a global map of air pollution, we don't know what causes the problem and how to tackle it most efficiently. And that's what we use models for. So here you see a model output. This is the column concentration, and top left is black carbon, which is also a warming pollutant in terms of climate forcing. Then upper right is particulate organic matter, and you see that two of them, these organics, are come together with burning processes from biomass burning, for example, but also from other burning processes. And then we have dust. I mean, if you look from space, you see particles, you also see dust, and this is a source that you cannot, or at least can very hardly control. And to the upper right, we see sea salt, same thing. Of course, this is mostly over the sea, but still, this is a source that we will not be able to control. The next one, sulfate. Sulfates have been mentioned, nitrates. These come mostly from fossil fuel combustion. Then ammonium, this comes from agriculture, this is to the lower left. And then if you put all these particles together, they absorb water, and depending on what is in the particles, you have more or less water in them, and you can see there's most water over the sea. So the particles over the sea are very hygroscopic, so they attract a lot of water, and they're more scattering, so they reflect more sunlight, but of course they're over the sea. Now, models, okay, model is only a model. Can be a useful model, but most models have problems. Of course, this model is no exception. But I have, by the way, for the discussion, if needed, many comparisons with data. I'm just showing this one for these three areas that are probably the most polluted ones on the globe. And you can see from these colors, the black colors are, by the way, the black dots are dust stations. To the left, we have the model. To the x-axis, we have the observations. And the ideal line would show ideal agreement, perfect agreement. Of course, you can never achieve perfect agreement. I would say this is pretty good agreement, but since it's our own model, I'll stay modest and call it reasonable agreement. So this is what you can do with a model. And of course, if you give model results, you should always be reminded of the fact that it is only a model. Now, maybe a bit technical, but I can go through this step by step. It is important to understand how these types of calculations are being made. So following the method of the global burden of disease to compute health outcomes is being shown here. So we have mortality, and then there is this Y0. This Y0 is the baseline mortality rates for a given population. So this is mostly known for countries, and sometimes only for regions, but often for countries, and for different disease categories. And the disease categories are ischemic heart disease, we also heard this morning, cerebrovascular disease, things that lead to heart attacks and strokes, chronic obstructive pulmonary disease, COPD, lung cancer, and acute lower respiratory illness. This is mostly in infants, LV. And actually this only occurs in the, say, low-income countries, because healthcare and better nutrition prevent it in high-income countries. Then we have population. Of course, this is another parameter that goes into the equation. We need to know where people are, where they are exposed to air pollution. And then we have these integrated exposure response functions, and they use the relative risk from which you calculate the attributable fraction. So we've heard this morning, if you have, for example, people dying from lung cancer or from stroke, there is a, say, 20% or 10% somewhere, an attributable fraction that goes to air pollution, to these diseases. So this attributable fraction is actually what's being directly used to compare with air pollution. And then it's not only PM2.5, it's also ozone. Now, this is an example of the sort of curves that you get. So to the left here, we have this attributable fraction as a function of PM2.5. And you see two curves here. And the upper one is the most recent one. And you can see these curves sometimes change. So the global burden of disease used the lower curve, so it went up. And so this is for chronic obstructive pulmonary disease for all ages. And so you get the attributable fraction as a function, and as a function of the pollution level. And what you can also see here is that if you go from, say, 100 micrograms to 80, the change in attributable fraction is not very large. But if you go from, say, from 20 to 10, the decrease is much stronger. So that also means that if you live in a very polluted environment, you must do a lot to get to the lower concentrations where you get the best, say, cost effectiveness of reductions. And what you can also see here, this is also something I would like to emphasize, is that if you put the WHO guideline onto this is 10 micrograms, you can see that especially with the new curves, which are based on more epidemiological studies, you can see there is quite a substantial part of the curve below the 10 microgram limit. So actually, I would also propose to WHO reconsider your guideline, because things have changed. And actually, we're now at something like four or so micrograms per cubic meter, which are really safe below that. So this is another issue that, unfortunately, this changed, but it means that we need to make strong reductions to get anywhere to clean air. Now, this is the estimated global mortality. So this is done with the output of our model. It's very close to the global burden of disease. So in total, we calculate almost 4.3 million deaths per year attributable to air pollution. The global burden of disease finds 4.5, so this is only outdoor air pollution. If you include indoor, you come to 6.5. This is the global burden of disease estimate. And you can see most is PM2.5, so 4.03, and ozone is something like 250,000. And to give you just a flavor of the uncertainty, it's about plus or minus 25%. This is the statistical uncertainty. And you can see ischemic heart disease and leading to heart attack is the number one, 1.4 million per year. COPD is the number two, about 1 million. Cerebrovascular disease leading to stroke is almost 1 million, and acute lower respiratory disease in infants is about 700,000, and lung cancer about 300,000. So these are our numbers. They slightly deviate from the global burden of disease, but not much. So I think that's a good indication. But we must use this because we need to use a model in order to look at the source structure. So this is another way of showing these results. So ischemic heart disease to the left is the number one, COPD, cerebrovascular disease. You can divide that also in ischemic and hemorrhagic stroke, leading to death, of course, and then lower respiratory disease in infants and lung cancer. So these diseases are actually pretty similar to the diseases you get from smoking. So I think we should call outdoor pollution passive outdoor smoking. So an update for 2015. So the mortality attributable to outdoor air pollution is about 4.3 million. Like I said, global burden of disease at 4.5. It is the main environmental health risk globally, and it's one of the top 5 overall health risks. So number one is high blood pressure, then diabetes, smoking, and being overweight. The number of years of life lost is actually a little bit higher, what we find, because we have taken updates for lower respiratory disease for children, which have become higher by the WHO. So we find that 120 million years of life are lost per year related to outdoor air pollution. And this also implies that each individual who dies prematurely, he doesn't or she doesn't lose a few weeks or so. No, these people lose 28 years of his or her life. This is a big number. And if you want to put that in perspective, you can see that the number of deaths from smoking is still larger, 6.4 million per year, according to the global burden of disease. But the number of years of life lost per individual affected is 24 years, because it doesn't affect children, at least not active smoking. And air pollution is 28 years. And the reason for the difference is also that especially when children die from air pollution, their life expectancy change is rather large. So there's large numbers. And now I've plotted here to the left the mortality related to air pollution in China, India, and in Europe together. Together, these countries or regions account for 67%, so it's 2/3 of the 4.3 million. So the 30 from China and the 21 India, etc., they add up to 67. So you see 30% is in China, 21% is in India, a smaller percentage is in Europe and Eastern Europe in particular. So EU, Europe, and North America. By the way, the largest growth is taking place in India. In China, it's now going down slowly. It's going slowly because of these curves that I've just shown you, so they have to go much further down. But India is the country with the largest growth numbers. And what's also interesting here, you see the per capita mortality in North America to the right, the EU, Europe, and then India and China, and the highest per capita mortality we find in Russia and the Ukraine. And this has much to do with the meteorological conditions there. They have no monsoon, for example, where sometimes the air is being cleaned by rain. Now you can make these sorts of maps, and it's also another thing I would like to emphasize is that you see cities here. So you can clearly see Delhi, you can also see New York, you can see Paris, London, and Moscow, etc., countries in East Asia. You see the cities. This is not because air pollution is confined to the city boundaries. The maps that Ram showed this morning, these large, brown clouds, these huge hazes, they're not local phenomena. They are large-scale phenomena. And the fact that these cities stick out in these maps here is that that's where most people live and get exposed to air pollution. So the attention for cities is justified because most people get exposed to air pollution in cities. But the attention to cities to control the problem is not justified because most of the air pollution actually, or a large fraction, depending on the city, comes from outside the city. So that brings me to the analysis of the source attribution. So again, the world here, this is now a global map with a slightly different scale, but you can see the hotspots in China and India. And this pie diagram now shows the world 4.3 subdivided in sources that contribute to this air pollution-related mortality. And the number one with more than 30% is residential energy use, mostly in low-income countries. But also a big part of the pie is agriculture, like it's ammonia coming from manure and over-fertilizing. Power production, of course, and then biomass burning, mostly. I apologize to the colleagues in South America, but the concentrations are not that high, but biomass burning in South America is very important, and also in Africa. And then also natural. We must also not forget that some fraction of the particulates that we see from space are natural, desert dust in particular. So this is sort of summarizing what are the leading sources here. So the source categories responsible for the largest impact on mortality. Now, obviously, over the Sahara and the Middle East, it's natural, it's dust. Leading does not mean more than 50%, but it's just the largest category. Over the United States, where this type of research, epidemiological research, is really the largest, or maybe next to Europe. But you can see that in the United States, it's power generation and traffic. And that also explains for the large interest in power generation and traffic. But if you go to other regions like India and most of Asia, where all the people live, including Japan, you see, or not Japan actually, but say Indonesia, Southeast Asia, some part is biomass burning, but most is residential energy use. That is really the leading cause of air pollution-related mortality. And then in Europe, you see green, that's agriculture. The leading source of air pollutants, PM2.5 in Europe, is agriculture. And this is because ammonia is a substance that reacts with other substances from traffic like nitrogen oxides and sulfates to make these particles. And what we did here in this model is take out these sources one after the other, and it simply appears that it is most efficient to reduce PM2.5 by reducing ammonia emissions in Europe. And in China and in India, it is residential energy use. And in Brazil and South Africa, it is biomass burning. So it's a rather heterogeneous picture. So it's not one cause and one solution. Also contrasting two countries like the United States. So these are the same pies now with causes of air pollution-related death. If you take these sources out, you get these pies. So you have in the United States, again, agriculture is important, but traffic, power production. If you put everything together that's related to fossil fuels, you get to 58%. Now the 26% was shifted a bit. This is the global average. But if you compare that with India, you see half is related to residential energy use and only 26% to fossil fuels. So fuels play a very important role for sure, but there are also other components, including natural ones, that should be kept in mind. So I have some conclusions. And outdoor air pollution causes respiratory cardiovascular disease and lung cancer, causing about 4.3 million premature deaths per year globally. Statistical uncertainty range are roughly 25%, mostly in Asia. So more than 70% of this 4.3 million, we calculate, is taking place in Asia. Residential energy use, household combustion emissions, which of course also contributes to indoor air pollution and related health problems. Residential energy is the dominant source category. And China and India together account for about half of all the air pollution related deaths worldwide. Fossil energy use, power production, industry, traffic is second largest if you put them together. Also because it is an important contributor to ozone, which is not the main cause of problems, but is an important cause of health problems. Then agriculture is the third one, mostly in Europe, but also in northeastern United States and East Asia. Major contributions to clean air could be made by reducing ammonia emissions. Then natural emissions are important, of course, in the Middle East, North Africa, etc. And then I also want to point out, coming back to this guideline 10 micrograms per cubic meter, which is the guideline for WHO. If you could implement that globally, it would reduce mortality attributable to air pollution by about 50%, which is a huge number. But also, I'm sorry, it's only 50%. We cannot be happy with 50%. It has to go further. So this is something that needs to be discussed. That's one more thing I would like to, this is very brief. This is something that was shown earlier, the Sustainable Development Goals. I think this is excellent that the United Nations, all countries have together decided to design these Sustainable Development Goals. Number 1 is no poverty, for sure. You see, number 6 is clean water. Actually, according to the Global Burden of Disease, 1.8 million people die per year because of bad water. And 4.3 or 4.5, according to Global Burden of Disease, a million people die per year because of bad air. Well, sorry, where's bad air here? It's locked into all of these things like health and maybe climate action. I think this is really an oversight that there's no clean air here. I'm sure this cannot be repaired, but I want to mention to you this anyway. I think we need clean air as a sustainable development goal, and I put it on number 13, but in terms of numbers, it actually should be before number 6. It is really a major issue, and I think there are technological and societal ways of dealing with this problem. Thank you very much.